In this video, we're going to talk about transformations of the function y equals x cubed and the function y equals x to the 4. Let's take a look at the function y equals x cubed. We see it there on our screen. We've got certain values in the table of values, and we graph those points, get the curve. Similarly, a quartic function, which means fourth degree, the function y equals x to the 4 looks like what you see there. Now, if the parent function is y equal x cubed, then the transformed function will be y equals, instead of cubing x, we'll cube k bracket x minus d, and then we'll multiply the result by a and add c. And similarly, if we're transforming the function y equals x to the 4, instead of raising x to the 4th exponent, we'll raise k bracket x minus d to that exponent. And then we'll multiply by a and we'll add c. So let's say we wanted to state transformations to y equal x cubed that give the curve shown there. Well, right away we see that we would like to factor the 3 out of the input. We do that. And now we can say a is 2, so we have a vertical stretch by a factor of 2. K is 3, so we have a horizontal compression by a factor of a third. D is 4, so we have a translation right 4 units. And C is also 4, we have a translation up 4 units. Now, what if we're given the curve shown here and we want to state transformations to the function y equals x to the 4? Well, one thing we'll do is we'll move the 5 to the other side, as you see here. We can rearrange the input, so instead of 6 minus 1/3 x, it's negative a third x plus 6. And then we can factor out the k value of negative a third. We multiply that by x minus 18. And so now we can say that we've got an a value of a half, meaning a vertical compression of a half, a k value of negative a third, meaning there's a reflection in the y-axis and a horizontal stretch by a factor of 3. We have a d value of 18, so we translate right 18 units. And we have a c value of 5, so we translate up 5 units. Now, we want to determine the equation of the curve shown, which represents a series of transformations to the curve y equals x cubed. Okay? Now, the first thing we want to do is figure out, we know that the parent function has a point of inflection at 0, 0. So let's find out what that point is for us, i.e. which point is the image of the point 0, 0 from the parent function. And 0, 0, and now you might say, well, why is that so important? Well, check this out. We know that the point of inflection of the parent function is 0, 0. Well, that 0, 0 will always map onto 0 over k plus d and a times 0 plus c. Well, 0 over k is 0 plus d is d. And a times 0 is 0 plus c is c. So whatever 0, 0 is on the parent function becomes dc on the transformed function. So that means dc on the transformed function is the point of inflection. And so that means wherever that point of inflection is, it immediately tells us our d value and our c value. And so since the point of inflection is at negative 3, 4, that means our d value is negative 3 and our c value is 4. Now, we want to determine the values of a and k. An interesting thing about odd functions, rotationally symmetric about the origin, is that transformations that can be described as a vertical stretch can also be described as a horizontal compression, and also vertical compressions can be described as horizontal stretches. So what that means is we can assign a value to either a or k and determine the resulting value of the other. So typically what we do is we let k be 1 and then we figure out what the resulting value of a will be. Now, this doesn't work for every function anywhere in the world because not every function is either even or odd, but this function happens to be an odd function, so it actually does work for this. So what we can do then is say we're going to let our k value be 1 based on the discussion earlier. D and C are the coordinates of the point of inflection, and so we just have to figure out what A equals. So we can say ultimately y equals A, and then x plus 3 quantity cubed plus 4. Well, how are we going to figure out what that A value is? In order to do that, we need to find one more point on the curve. And we see that one of the points on the curve is this point negative 5, 2. Now, we can't sub in the point negative 4, 3. We've already used that, so that's not eligible for this process. But we could sub in the point negative 5, 2. Or if we prefer, we could sub in the point negative 1, 6. Oh, and I said negative 4, 3. I should have said negative 3, 4. But that's not available to us anymore anyway. We could sub in the point negative 1, 6. Let's sub in the point negative 5, 2. So subbing in a negative 5 for x and subbing in a 2 for y, we end up solving for y. That 2 is equal to negative 8a plus 4. Ultimately, a is a quarter. And so therefore, we can say that an equation of this curve is y equals 1/4 times the quantity x plus 3 cubed plus 4. Now, what if we want to determine an equation of a curve shown representing a series of transformations to the curve y equal x to the 4? Well, first we want to find out which point is the vertex. Very similar to the discussion we just had about odd functions. It works with even functions as well. But before we get into that, let's just talk about how on the parent function of y equal x cubed, x to the 4, sorry, we know that the vertex is always at 0, 0. When we go to transform that vertex, that 0, 0 will always map onto D and C. And so whatever the vertex point is, gives us the values of D and C. Okay? Well, we look at the vertex point here and we see, well, that's the point 3, 8. So we can say D is 3 and C is 8. Now, we also have to find the values of A and K, and this is where the conversation is very similar to the one we had in the last section. This is an even function, and so transformations that can be described as a vertical stretch can also be described as a horizontal compression, and vertical compressions can be described as horizontal stretches. And so basically, as a result, we can assign a value to either A or K and determine the resulting value of the other. Usually we let K equal 1 and solve for A. And so we're going to let K be 1 here. And we know D has to be 3 and C has to be 8. And we're going to find a value for A. And this is our equation so far is A bracket x minus 3 quantity to the 4 plus 8. Okay, now we want to sub in any other point that we know to be on this curve. We could sub in the point 2, 5. We could sub in the point 4, 5. We choose the point 4, 5. 5 equals A times 4 minus 3 quantity to the 4 plus 8. In other words, 5 equals A plus 8, meaning A is negative 3. And so one equation for the curve that's shown is the equation y equals negative 3 times the quantity x minus 3 to the 4 plus 8. Now, if you're determining so in summary, if you're determining the equation of a curve that's a transformed version of the parent function y equal x cubed, remember that the transformed function has the form y equals a k x minus d cubed plus c. The point of inflection of the transformed function is at dc. We can let k equal 1 and then plug in another point to solve for a. Very similarly, if you're determining the equation of a curve that's a transformed version of the parent function y equal x to the 4, remember the transformed function has a very similar equation. Instead of raising it to the exponent 3, we raise it to the exponent 4. The vertex is at DC. We let k equal 1 and plug in another point to solve for a. This process will work for these sorts of questions. Now let's talk about intercepts. First, Y-intercepts. Every polynomial function in the world has exactly one Y-intercept. So that means if we have a question in this section where we're asked for the Y-intercept of a transformed cubic function or transformed quartic function, we know we're going to get one answer. Why is that? Because every polynomial function is defined over all real values of x. This means you can sub in an x value of 0 and get a valid answer. But because it's a function, there's only going to be one such answer, and therefore we're going to have exactly one Y-intercept. Now, let's talk about X-intercepts for cubic functions. No matter where you transform and stretch a cubic function, reflect it, compress it, however we might do it, we're going to have one X-intercept. And perhaps these diagrams somehow make that clear. In every one of these cases, there's one X-intercept. So like it says at the bottom, no matter how you transform the parent function, you'll have one X-intercept. That's because the end behaviors of the parent function range from y goes to negative infinity to y goes to infinity, or vice versa, and also because there are no turning points. Now, as for X-intercepts of transformed y equal x to the 4 curves, in other words, quartic curves, in that case, you could have 0, 1, or 2 X-intercepts as shown. You could have 2 X-intercepts in either of the first two cases, or you could have 1 X-intercept in either of the next two cases, or you could have no X-intercepts at all as shown in the next two cases. Okay? So when dealing with a transformed y equal x cubed curve, there will be one X-intercept and one Y-intercept. When dealing with a transformed y equal x to the 4 curve, there will be 0, 1, or 2 X-intercepts, and there will be one Y-intercept. So suppose we're asked to determine the X and Y intercepts of the curve shown. We know that since it's cubic, a transformed y equal x to the 3 curve, we know there's going to be exactly one Y-intercept and one X-intercept. So to determine the Y-intercept, this is usually thought of by most students as pretty easy. We're simply going to let x equal 0. We plug a 0 in for x to the equation and follow our steps of Bedmas. We're going to have to cube the number negative 12, which gives us negative 1,728. Multiply that by negative 2 and add 16. We ultimately get a y-intercept of 0, 3,472. Now, how about the x-intercepts? Well, or x-intercept singular. To determine the x-intercept, we're going to let y equal 0. So we let y equal 0. We'll subtract 16 from both sides, which gives us this line shown. And we're going to divide both sides by negative 2. And so that ends up letting us know that 8 is equal to 3 times x minus 4 quantity cubed. Now we'll take the cubed root of both sides. You might be used to situations where if you're told x squared is equal to a number, you always put a plus or minus in front of the square root. We do not put a plus or minus in front of a radical sign when you're introducing an odd root to solve an equation. In this case, erasing this, in this particular case here, back on the left-hand side, I'm going to take the third root of 8, and I'm going to say that that equals 3 times x minus 4. We do not put a plus or minus there. There aren't two different possible answers. There's only one. We say the cubed root of 8 is equal to 3 times x minus 4 without the plus or minus in front. The cubed root of 8 is equal to 2. 2 is equal to 3 times x minus 4. And just really quickly, in case you're curious, well, why don't you put a plus or minus in front? Imagine if we put a negative 2 down instead of a positive 2 like we have here. That would be saying that negative 2 quantity cubed is equal to 8. But that's not true. So we don't do it. So short version is we say positive 2 equals 3 times x minus 4. So we divide both sides by 3. We say 2/3 equals x minus 4. Adding 4 to both sides gives us x equals 14/3. So the only x-intercept is 14/3, 0. Now, what if we have a quartic and we want to determine the x and y intercepts of that curve? Well, let's start by finding the y-intercept. We know there's always going to be one y-intercept. To do that, we let x equal 0. We plug that 0 in right here. And then we follow the steps of Bedmas. 0 minus 5 is negative 5, but we're multiplying it by a half, so we've got negative 5 over 2 quantity to the 4. Negative 5 over 2 quantity to the 4 is equal to 625 over 16. Okay, now we're going to multiply that by 5 and subtract 80. And we ultimately get 1,875 over 16. That is our y-intercept, 0, 1,875 over 16. Okay, now how about for x-intercepts? Well, as stated earlier, when you have a fourth degree, you could have 0, 1, or 2 x-intercepts. We don't know which yet. Let's find out. We're going to let y equal 0. So putting a 0 here, we move 80 over and divide both sides by 5. So when we move that 80 over, it becomes positive. Divide both sides by 5, we get 16. Now, we're going to take the fourth root of both sides. Now we do put a plus or minus in front of the radical sign because we're introducing an even root. So we'll get to why that is in a minute, but we put plus or minus the fourth root of 16, and that's equal to 1/2 times x minus 5. Because as we had in the previous one, we take the fourth root of both sides, and it'll leave us with the interior. Okay, and so the fourth root of 16 is 2, so we have plus or minus 2 is equal to 1/2 times x minus 5. So we say either negative 2 equals 1/2 times x minus 5, or we say positive 2. There should be a positive 2 there, equals 1/2 times x minus 5. That's a little typo. Should say positive 2. Now, you might be wondering, well, why can we say that here, plus or minus? And here's why. If I said to you, go back to what we had written on the last page. We had 16 equals 1/2 and then x minus 5 to the 4. So 16 was equal to 1/2 x minus 5 quantity to the 4. If I let, when I take that fourth root, if it's a negative 2 and I raise that to the exponent 4, I do get 16. So I need to consider that possibility. Or if I think of 2 to the exponent 4, I also get 16, so I have to consider that possibility. So it has to do with being an even root, the fourth root, as opposed to the third root like it was last time when we didn't put the plus or minus in front. Okay? So we have, if you go back to what we had here, I'll pick it up from this point. Negative 2 equals 1/2 times x, the quantity x minus 5. Or positive 2 equals 1/2 times the quantity x minus 5. We divide both sides by 1/2. We get negative 2 over 1/2 is x minus 5, or positive 2 over 1/2 is x minus 5. So negative 4 is x minus 5, or positive 4 is x minus 5, meaning x is 1 or x is 9, meaning there are x-intercepts at 1, 0, and 9, 0 for this curve. Now, let's see if we can find x-intercepts, if any, of that curve there. This one's not actually asking us to find the y-intercepts. Y-intercept, there's only one. It would be pretty easy. We just sub in an x value of 0 and evaluate. But let's see if we can figure out if there are any x-intercepts. Well, we'll let y equal 0. So this is let 0 equal that expression. If we divide both sides by negative 3, we just get 0 equals x plus 7 quantity to the 4. We'll take the fourth root of both sides and we'll put a plus or minus in front of the radical sign because it's an even root. So we determine plus or minus the fourth root of 0 is equal to x plus 7. The fourth root of 0 is 0. So we have plus or minus 0 is equal to x plus 7, but there is no positive or negative 0. 0 is just 0. So 0 is equal to x plus 7. X is negative 7. So this is one of those situations we talked about where there's only one x-intercept. And now let's see a situation where there are no x-intercepts at all, what that would look like. Pretend you're given this function here. You want to determine the x-intercept, so you're going to let y be 0. Okay, now once you let y be 0, you're going to move that 8 over, like we have here, and you're going to divide both sides by -5, like we have here. We're now going to take the fourth root of both sides, and because it's an eventh root that we're introducing, we put a plus or minus in front, and we have this expression right here. But you cannot take the fourth root of a negative quantity. There's no way you can come up with any number, whether positive or negative, multiply it by itself 4 times and come up with a negative quantity. That is impossible. You can take the third root of a negative quantity, but you cannot take the fourth root of a negative quantity. So since we cannot do that, there are no x-intercepts in this curve.